Hi everyone, today we'll be looking at paper 2 Pure Mathematics in October 2021. Question 1, we are told that we've got an arithmetic series. The first term is 16, the 21st term is 24. We need to find the common difference. So we know that A, the first term, is 16. We know that U21 is 24, and this is A plus n minus 1 D. We take into account that A is 16, so 24 is 16 plus 20D, leading to 8 is 20D, and therefore D is 8 over 20, which simplifies to 2 over 5. B, hence find the sum of the first 500 terms of the series. I need to use the summation formula here. So the sum of the first 500 terms will be n over 2, 2a plus n minus 1 d. I'll plug everything on the calculator, and this gives an answer of 57,900. In question 2, we've got the functions f and g defined here, and we need to state the range of f in part A for a mark. Well, we start by observing that the x squared will be greater than or equal to 0 for all x in the real numbers. So if I multiply by -2, I can conclude that -2x squared will always be less than or equal to 0. So 7 minus 2x squared will be less than or equal to 7. And so y is less than or equal to 7. This is the range of f. Alternatively, you could have just seen that it's always 7 minus something which is non-negative. So it's 7 or below, leading to y being less than or equal to 7. In B, we need to find g of f of 1.8. It's a composite function here. So g of f of 1.8, we always start from the inside, so I will evaluate f of 1.8 and then input it into g. So I'm going to say that this is g of 7 minus 2 times 1.8 squared, which is g of 0.52. And then I will input 0.52 into g. So this is 3 times 0.52 over 5 times 0.52 minus 1, which gives an answer of 0.975. And then C, we need to find the inverse of g. So we need to find that function which is undoing whatever g is doing. So I will start by writing it as y is equal to 3x over 5x minus 1. That is a standard approach here. We interchange x and y. So wherever we see a y, we put an x. Whenever we see an x, we put a y. And then we try to make y the subject of the formula. I will cross multiply to get 5yx minus x is 3y. I will collect the y's on the left-hand side, so 5yx minus 3y is equal to x. I will factor out the y, giving me y brackets 5x minus 3 is equal to x. And then it's easy to see that y is x over 5x minus 3. Now, we don't stop here. We could be penalized with a mark if we actually stop here. We need to actually state that g inverse of x is equal to x over 5x minus 3. In question 3, we need to use the laws of logarithms to solve this equation. Now we know that if we've got log of something minus log of something else to the same base, in this case 3, I can write this as the log of the quotient. So log of 12y plus 5 over 1 minus 3y to the base of 3 is equal to 2. Which means that 3 squared is 12y plus 5 over 1 minus 3y. So 9 is 12y plus 5 over 1 minus 3y. I will cross multiply to get 9 minus 27y is 12y plus 5, leading to 4 is equal to 39y, and therefore y is 4 over 39. Question 4, we are being given that theta is small and measured in radians, and we need to use the small angle approximations to show that this is true, finding the values for integers a, b, and c. Now we know that in the formula sheet, we are told that if theta is small and measured in radians, then sine of theta is approximately theta, and cos theta is approximately 1 minus theta squared over 2. So this means that 4 sine of theta over 2 plus 3 cos squared theta is approximately 4 times theta over 2 plus 3 times 1 minus theta squared over 2 squared. So I will expand this. I obviously get 2 theta plus 3 times 1 minus theta squared plus theta to the power of 4 over 4, which further simplifies into 2 theta plus 3 minus 3 theta squared plus 3 theta to the power of 4 over 4. Now, I see that the expression I need to arrive at does not include the theta to the power of 4. It actually goes up to determine theta squared, so I could include higher order terms. So this is just 3 plus 2 theta minus 3 theta squared, which means that A is 3, B is 2, and C is negative 3. Question 5, we've got this curve C. It's actually a quartic in x. We need to find the y dx and then the 2y by dx squared. So simple differentiation here. So for dy dx, we get the power down. We deduct 1 from the power. So it is 5 times 4, 20x cubed minus 72x squared plus 84x minus 32. And then a further differentiation for the second derivative, the 2y by the x squared is 60x squared minus 144x plus 84. So this is the first and the second derivative. And then in part B, we need to verify that C has a stationary point at x is 1. Now, one of the key words that could be using the verify means that I just need to show that when x is 1, we have a stationary point. And the stationary point simply means that we've got dy dx being 0. So I will actually start by evaluating dy dx at x is 1, which is 20 times 1 cubed minus 72 times 1 squared plus 84 times 1 minus 32, which is 20 minus 72 plus 84 minus 32, which is 0. Therefore, C has a stationary point at x is 1. Now, two things to note here. The first one is that you need to explicitly show the substitution of x is 1 and u arriving at 0. So this has to be shown. You can't simply write dy dx at x is 1 is 0. You need to show the working out. And you also need to write the conclusion. The fact that dy dx is 0 tells me that C has a stationary point at this x is 1 value. In II, we need to show that this stationary point is a point of inflection, giving reasons for your answer. Now, for a point of inflection, it is necessary that we've got a change in curvature around that point. So what we need to do here is investigate the second derivative, whether it's positive or negative, in the vicinity, in the neighborhood of x is 1. So to do this, I simply need to come up with a table here of x and the 2y by the x squared. We need to investigate around 1, so I could go a bit to the right and a bit to the left, so maybe 0.9 and 1.1. So I will evaluate the second derivative when x is 0.9. This gives me a value of 3. I will evaluate the second derivative when x is 1.1. This gives me a value of negative 1.8. I could even evaluate it at x is 1. It gives me a value of 0. What we notice, however, is that we have a change in sign. It goes from positive to negative. We know that if it's a positive, then it is convex. And if it's negative, it's concave. So we've got a change in curvature, which is exactly the necessary condition for a point of inflection. So I need to state change in curvature hence at x is 1 we have a point of inflection. So we always need to come up with this table, investigate the sign of the second derivative to the left and the right of what we believe to be a point of inflection, and if it is indeed positive to negative or negative to positive, then we need to state change in curvature and conclusion. In question 6, we've got the figure shown here. It's composed of 3 sectors. The 2 smaller sectors are congruent, and we need to write down in terms of theta the size of the angle AOB, which is the angle here. We are obviously in radian mode, so all of this here is pi. Since the 2 sectors are congruent, then the 2 angles here are equal, and therefore the angle we are after is just pi minus theta over 2. In B, we need to show that the area of the logo is given by the expression shown here. So we're just going to use the fact that the area of a sector is a half r squared theta, provided that theta is in radians. So we've got the big sector here, CDO, plus twice the sector AOB. So the total area will be a half times the big radius, which is 2r all squared times theta, plus 2 times a half r squared times the angle, which is pi minus theta over 2, as we have found in part A here. We proceed in simplifying this. We get a half times 4r squared theta plus the 2 cancels out, r squared times pi minus theta over 2. We know that the half r squared will be a common factor here, so I will take the half r squared, and I'm left in the bracket with 4 theta plus pi minus theta, which is simply a half r squared 3 theta plus pi as required. Then in part C, we need to find the perimeter of the logo, giving our answer in simplest form in terms of r, theta, and pi. Well, the perimeter will simply be the length of the arc here twice, because we've got the identical part here. The bigger arc, which is this one here, and then we need to add up the straight line parts, this, and this. Now, obviously, AF is 2r. ED is r, this is r, and we also know that the length of the arc is r theta when theta is in radians. So the total perimeter will simply be the length of the bigger arc, which has a radius of 2r and an angle of theta, plus twice the length of the smaller arc, which is r times pi minus theta over 2, plus the 2 straight line parts, which was r, and then the bottom horizontal part, which was 2r. So this gives me 2r theta plus the 2 with the 2 cancel out. So it's r pi minus r theta plus 4r, leading to r theta plus r pi plus 4r. It has to be in terms of r, theta, and pi. In question 7, we've got a sketch of part of this curve. The point P5, negative 13, lies on the curve, and we've got a tangent to C at P. we're being asked to use differentiation to find the equation of L, the tangent, giving our answer in the form y cos mx plus c. So we will start by differentiating. So it's a polynomial, so we simply get the power down, deduct 1 from the power to get 3x squared minus 20x plus 27. We then evaluate dy dx at x is 5 in order to get the gradient of the tangent at this specific point. So it's 3 times 5 squared minus 20 times 5 plus 27, which gives an answer of 2. So to find the equation of the tangent, we use y minus y1 is mx minus x1. I still need to expand and make y the subject, so y plus 13 is 2x minus 10, leading to y being 2x minus 23. It then in part B says, hence verify that L meets C again on the y-axis. So I will just substitute x is 0 for both the straight line and the curve. So when x is 0 for the tangent, the straight line, we get y is 2 times 0 minus 23, which is negative 23. And for the curve, when x is 0, we get y is 0 cubed minus 10 times 0 squared plus 27 times 0 minus 23, which is also negative 23. Hence, the line L and the curve C meet again on the y-axis at 0, negative 23. It was a show that question. We need a conclusion. So this is the conclusion we have to write down to claim full marks. And then C, I need to use algebraic integration to find the exact area, which is the area shown shaded here in gray. So we know that it's the area enclosed above by the curve, below by the tangent. So I will simply say that the area R will be given by the integral from 0 to 5 of x cubed minus 10x squared plus 27x minus 23 minus the straight line, which is 2x minus 23 dx. Notice the brackets here to avoid messing up with the negative signs. I will simplify first of all within the integral to get x cubed minus 10x squared plus 25x dx. And then I will integrate. I increase the power by 1, divide by the new power. So minus 10x cubed over 3 plus 25x squared over 2. My limits are 0 and 5. I show the substitution of the lower limit, which is 5 to the power of 4 over 4 minus 10 times 5 cubed over 3 plus 25 times 5 squared over 2. And then the substitution of the lower limit will simply result in a 0. So plug this on the calculator and get 625 over 12 units squared. In question 8, we've got a curve being described here in terms of P and Q constants, and we need to show that dy dx takes this form. Obviously, I need to use implicit differentiation. So from left to right, we differentiate with all the usual rules. If we happen to come across a term that contains y that we differentiate, then I put a dy dx term as well. So my starting point is px cubed plus qxy plus 3y squared is 26, which means that 3px squared plus qy, it's the product rule here, plus qx dy dx plus 6y dy dx is 0. I will collect the dy dx terms on one side, the rest on the other. So dy dx brackets qx plus 6y is equal to minus 3px squared minus qy, which means that dy dx is minus 3px squared minus qy, and all of it over qx plus 6y. So this means that if I compare with the printed answer, it must be the case that A is negative 3, B is negative 1, and C is 6. In part B, I need to find the value of P and the value of Q, given that we've got the point P with coordinates negative 1, negative 4 lying on C, and that the normal at P has this equation here. I will actually start from this second piece of information because I can rearrange the equation of the normal in order to recover the gradient of the tangent. So, starting from 19x plus 26y plus 123 is 0, we can say that 26y is minus 19x minus 123. So if I divide throughout by 26, I get that y is minus 19x over 26 minus 123 over 26. The gradient of the normal is minus 19 over 26, which means that the gradient of the tangent will be 26 over 19. Remember, these two numbers should be multiplying out to negative 1. So, dy dx now at x is negative 1 and y is negative 4, I will substitute this into the expression we obtained above to give me minus 3p times minus 1 squared minus q times minus 4, and all of it over q times negative 1 plus 6 times negative 4, which simplifies to minus 3p plus 4q over minus q minus 24, and we know that this must be equal to 26 over 19. So all of this simply deriving from the fact that we were given the equation of the normal. Now, I will cross multiply to get that 19 times minus 3p plus 4q is equal to 26 times negative q minus 24. I will expand minus 57p plus 76q is minus 26q minus 624. So minus 57p plus 102q is minus 624. Now, we also know that the point P with coordinates x is minus 1 and y is minus 4 lies on the curve. So when x is minus 1, y is negative 4. And this means I can substitute x is negative 1 and y is negative 4 into the equation of the curve. So this will give rise to a second equation in P and Q, which will lead to simultaneous equations in P and Q. So we get minus P plus 4Q plus 48 is 26, which means that 4Q plus 22 is P. These are the two equations we were after. I will substitute 4Q plus 22 in the place of P here. So minus 57 times 4Q plus 22 plus 102Q is minus 624, which means that minus 228Q minus 1254 plus 102Q is minus 624. So simplifying this into minus 126Q is 630. So Q must be 630 over negative 126, which is negative 5. To find P, I will simply substitute the value of Q of negative 5 into this expression here. So we get that P is 4 times negative 5 plus 22, which is 2. In question 9, we need to show that this sum from n is 2 up to infinity gives me a result of 9 over 28. Well, the only way of evaluating a sum to infinity is for this to give rise to a geometric sequence. So I think it's a good idea to start by substituting the first few values for n to see exactly what's happening. So when n is 2, we get 3/4 squared times cos over 180 times 2, which is equal to 9 over 16. When n is 3, we get 3 over 4 cubed times cos over 180 times 3, which is minus 27 over 64. When n is 4, we get 3 over 4 to the power of 4 times cos over 180 times 4, and this is equal to 81 over 256. It doesn't take long to realize that we're looking at a geometric sum. The first term being the 9 over 16. So the A is 9 over 16. And the common ratio will simply be the next term over the previous term. So I do this. The minus 27 over 64 divided by 9 over 16 to give me the result of 3/4. That is the ratio, that is the number by which we multiply to go from the one term to the next term. And now that I've got all of this information, I can simply say that the sum from n is 2 up to infinity of 3/4 n times cos of 180 n is a over 1 minus r, and this gives a value of 9 over 28 as required. Question 10, we've got the time, capital T seconds a pendulum takes to complete one swing. It's given by this formula. T is A, L to the B. L is the length of the pendulum in meters, and the A and B are constant. So we need to start off by showing that this relationship can be written in this form. So I will actually start by writing out the model given. We have that capital T is A, L to the B. I will take log base 10 of both sides. So log T is log of A, L to the B base 10. So log T base 10 is log of A base 10 plus log of L to the B base 10. It's the product rule of the logarithms. And then log of T base 10 is log of A base 10 plus B log L base 10, which is exactly what I had to show. We then have a student who carried out the experiment. They have plotted log T against log L, and it seems to be a linear relationship with a straight line passing through these 2 points. We need to find a complete equation of the model. So my starting point will be exactly by considering these 2 points which are given, the minus 0.7, and the 0.21, 0.45. I will start by finding the gradient. So I will do y2 minus y1 over x2 minus x1. And this gives an answer of 45 over 91. So y minus y1 is mx minus x1. So this leads to y is 45 over 91x plus 9 over 26. This is the equation of the straight line. Now recall that we have found that log of capital T base 10 is B log L base 10 plus log of A base 10. So we can compare the constant here matches the log a base 10, and the coefficient of x, the gradient, will simply be b. So we can say that the b is 45/91, which to 3SF is 0.495, and log of a base 10 is 9/26, which means that a is 10 to the 9/26, which is 2.22. So this means that the final model is capital T is 2.22 L to the 0.495. And then part C, with reference to the model, interpret the value of the constant A. A is the 2.22 we found here, and we can see that when L is 1, then capital T is 2.22. Now, L was the length of the pendulum. If L is 1, this means that the length of the pendulum is just a meter. So we can simply say that when the length of the pendulum is a meter, then the time to complete one swing is 2.22 seconds. So the time to complete one swing is 2.22 seconds. So it has to be in context. We need to refer to the pendulum, to the length. We need to include units, the time to complete one swing. Everything has to be in context here. Question 11, we've got a sketch of the graph with equation y is the modulus of 2x minus 3k. And we need to sketch the graph with equation f of x is k minus the modulus of 2x minus 3k. We need to show the coordinates of the maximum point and then it cuts on the axis. So I always like to start by splitting what I have been given. So I will start with f of x is k minus the modulus of x, of 2x minus 3k. We always split in two cases. So if 2x minus 3k is greater than or equal to 0, then the modulus sign behaves like a normal set of brackets. And if it's negative, if 2x minus 3k is negative, then we've got a change of the sign outside. So we see it's the union of two straight lines which simplify into 4k minus 2x. If x is greater than or equal to 3k over 2, and it's minus 2k plus 2x if x is less than 3k over 2. Now obviously something magical happens at x is 3k over 2. We have the vertex, so our vertex is found at x is 3k over 2. This is the point at which this bracket is 0, and therefore f of x is k, so the y value will be k. So we can now proceed in sketching this graph. As you can see, I've drawn the graph here. We start with the vertex at 3k over 2, k. We've got the straight line going uphill to the left and the straight line going downhill to the right. We have found the cuts on the x-axis by setting y is 0 and the cut on the y-axis by putting x is 0. So we've got all the necessary information to claim the full marks for this part. And then for part B, we need to find in terms of k the set of values of x for which this part is greater than x minus k. This is obviously f of x. So I will be adding the line y is x minus k to see exactly what's happening. So this is a straight line going uphill, cutting through the x-axis at k and the y-axis at negative k. So this is y is x minus k. So we want to find when is our original graph f of x above the line. So it's obviously this part here. So we've got one cut, it's at x is k. We need to find the other cut. this one here, and we will do that by equating x minus k with 4k minus 2x. So I will equate k 4k minus 2x with x minus k. We get that 5k is 3x, and therefore 5k over 3 is equal to x. So this is the point here. I will add on my diagram just to have all the information. It's 5k over 3, and therefore I can conclude that the solution, the set of values that satisfy the given inequality, is all x such that x belongs to the reals, and the x is between k and 5k over 3. We had to give our answer in set notation, so it is a necessary requirement to have this x semicolon in order to match the set notation. And then part C, we need to find in terms of k the coordinates of the minimum point of the graph with this equation. So we really need to consider the transformations and how these affect the x and the y's. So I'll start by writing out what we have been given. Y is 3 minus 5 f over half x. So let's start with the 3 here. The 3 means we add 3 to y. Then the negative 5 means I will multiply y by negative 5, and then a half within the bracket here means I will multiply x by 2. So we will apply these transformations on the vertex, which was at 3k over 2 comma k. So if we start from 3k over 2 comma k, then let's consider on how the x and the y get affected. The x will be multiplied by 2, which will give me 3k, and then the y will be multiplied by negative 5, and then we add 3. So if I multiply y by negative 5, I go to minus 5k, and then I add 3. So the y value will be minus 5k plus 3. In case you are wondering on how we started off from a maximum point and we ended up to a minimum point, because this one here was a maximum point, the negative in front of the 5 means it's a reflection along the x-axis, which is turning it upside down, and therefore we're looking at a minimum. In any case, the answer should be 3k, minus 5k plus 3. In question 12, we need to use the substitution u is 1 plus root x to show that this integral from 0 to 16 with respect to x leads to this integral with respect to u. So this integration by substitution, we are told that u is 1 plus root x. The first thing I'll do is attack the limits. So when x is 0, we see that u must be 1, and when x is 16, we get that u is 1 plus root 16, which is 5. Now, I will say that u minus 1 all squared is x, which means that 2 times u minus 1 du is dx. So I know what to put in the place of dx. I know what the limits get translated to, which means that the integral from 0 to 16 of x over 1 plus root x dx will be the integral from 1 to 5. In the place of x, I will put u minus 1 squared. In the place of 1 plus root x, I will put u. And in the place of dx, I will put 2 brackets u minus 1 du. So what I need to do now, write this as the integral from 1 to 5 of 2 brackets u minus 1 cubed over u du, with p being 1 and q being 5, the limits in the integral with respect to u. It then says, hence show that the integral is a minus b ln 5, where a and b are constants to be found. I will actually start by considering what needs to be integrated, which is 2 brackets u minus 1 cubed over u. I will expand this as 2 brackets u cubed minus 3u squared plus 3u minus 1, all of it over u, which leads to 2u squared minus 6u plus 6 minus 2 over u. And therefore the integral from 1 to 5 of 2 brackets u minus 1 cubed over u du is simply the integral from 1 to 5 of 2u squared minus 6u plus 6 minus 2 over u du. This will lead to 2u cubed over 3 minus 6u squared over 2 plus 6u minus 2 ln u from 1 to 5. Now the 6 with the 2 simplified to a 3 in the numerator, and then I substitute the upper limit and then the lower limit. So this will give me 2 times 5 cubed over 3 minus 3 times 5 squared plus 6 times 5 minus 2 ln 5 minus brackets 2/3 minus 3 plus 6 minus 2 ln 1. Now we know that ln of 1 is simply 0. So if I simplify everything, I get 250 over 3 minus 75 plus 30 minus 2 ln 5 minus 2/3 plus 3 minus 6, which leads to 104 over 3 minus 2 ln 5, which matches the form given. In question 13, we're being given that the curve is described parametrically as x is sine 2 theta and y is cosec cubed theta, and we need to find an expression for dy dx in terms of theta. So we know that we need to find dx d theta and dy d theta. So dx d theta will simply be the derivative of the inside, which is 2, times the derivative of sine, which is cos, so 2 cos 2 theta. And for y, which is cosec cubed theta, I will simply do get the power down, 3, deduct 1 from the power, cosec squared, times the derivative of cosec, which is minus cosec theta cot theta. This gives me minus 3 cosec cubed theta cot theta, and therefore dy dx is simply dy d theta over dx d theta. So this will be minus 3 cosec cubed theta cot theta over 2 cos 2 theta, and this completes part A. B, hence find the exact value of the gradient of the tangent to C at the point where y is 8. So we need to evaluate dy dx when y is 8. I need to find the corresponding value for theta. So if y is 8, this means that cosec cubed theta is 8. So 1 over sine cubed theta is 8, which means sine cubed theta is 1 over 8, and therefore sine of theta is a half. Now we have that theta varies between 0 and pi over 2. It's an acute angle. We know that the angle which has its sine being a half is pi over 6. So this simply means that theta is pi over 6. So when theta is pi over 6, we substitute into dy dx. It's going to be minus 3 cosec cubed of pi over 6 cot of pi over 6 over 2 cos 2 pi over 6. And plugging this on the calculator is giving an answer of negative 24 root 3. In question 14, we've got water flowing in at a constant rate into a large tank. This is happening at a rate of 0.48 cubic meters per minute. So we can call this the dV dt in. So this is the volume that goes in, which is 0.48. At the same time, we've got water flowing out at 0.1 h cubic meters per minute. So this is dV dt out, 0.1 h. And we need to show that according to this model, this is the differential equation being satisfied. So we will actually start by saying that the rate of change of volume, so dV dt, is simply what goes in minus what goes out. At the same time, we know that the volume of this is given by the base area, which is 3 times 8 times the height, which is 24h. So dV dH is 24. And therefore, we can say through the chain rule that dH dt is dH dV times dV dt. So dH dV is simply the reciprocal of dV dH, which is 1/24, times dV dt, 0.48 minus 0.1 h. I will multiply everything by 24 to get that 24 dH dt is 0.48 minus 0.1 h. I will then multiply everything by 50, and we see that we obtain that 1200 dH dt is equal to 24 minus 5h as required. In case you are wondering on where the 50 came from, I simply observe that the 0.1 to become 5, it means that we need to have multiplied this by 50, and I see that I obtain the rest of the terms as stated in the answer. And then part B, show that according to the model, this is the expression for h in terms of t. I will actually separate the variables here to get that the integral of 1200 over 24 minus 5h dh is equal to dt. So the left hand side is simply going to give me something in terms of ln. I need to divide by the derivative of 24 minus 5h, so negative 5. ln 24 minus 5h is equal to t plus c. Now the 1200 with the 5 leave me at 240 in the numerator. We know that when t is 0, h is 2. This was given in the question. So minus 240 ln of 24 minus 5 times 2 is equal to 0 plus c. And therefore minus 240 ln 14 is c. This means that minus 240 ln of 24 minus 5h is equal to t minus 240 ln 14. And now I need to rearrange in order to match the form of the answer. So I will start by saying that minus t is 240 ln of 24 minus 5h minus 240 ln 14. I will divide by 240 to get minus t over 240 is ln of 24 minus 5h minus ln 14. And then I can combine the two logarithms on the right by writing as ln of 24 minus 5h over 14. I will remove the ln by writing it as e to the minus t over 240 is 24 minus 5h over 14. And I will now cross multiply to get 14 e to the minus t over 240 is 24 minus 5h. So 5h is 24 minus 14e to the minus t over 240, and the final step is simply to divide everything by 5. This leads to h is 24 over 5 minus 14 over 5 e to the minus t over 240. That is the expression for h in terms of t. Part C, given that the tap remains open, determine according to the model whether the tank will ever become full. So we know that the height of the tank is 5 meters, so the question is whether the height can ever reach 5. So we can consider long-term behavior. So as t tends to infinity, we have that e to the minus t over 240 has to go to 0, because e to a very large negative power is something very small, close to 0. Hence, h tends to 24 over 5, which is 4.8, because essentially this term here drops dead and I'm left with 24 over 5. And I have to say that since 4.8 is less than 5, the tank will never become full. We need to give a reason. The reason is this limiting investigation as t goes to infinity, what happens to h, and therefore a conclusion at the end to complete the answer. In question 15, we need to express 2 cos theta minus sine theta in the form r cos theta plus alpha, where r is positive and alpha is an acute angle in radians. So this is a standard opening part of such a question. We've got 2 cos theta minus sine theta to be written as r cos theta plus alpha. I use the addition formula for r cos theta plus alpha to write it as r cos theta cos alpha minus r sine theta sine alpha, and then I equate the cos theta terms and then the sine theta terms in order to find the value of r and the value of alpha. So we've got that 2 is r cos alpha, and we've got that 1 is r sine alpha. This means that 2 over r is cos alpha and 1 over r is sine alpha. I could draw a triangle at this stage, and we've got that this here is alpha, the cosine is 2 over r, and the sine is 1 over r, which means Pythagoras theorem gives me that r is 1 squared plus 2 squared square root, so it's root 5, and tan alpha is a half, which means that alpha is 0.464 to 3 decimal places. So we can conclude that 2 cos theta minus sine theta is root 5 cos of theta plus 0.464. In B, we've got this modeling question. We are modeling the point P at the end of one of the paddles of the wheel. We are modeling the height of P, h meters above the water level through this equation here. And we need to use this model to find the maximum height of P above the water level, as well as the value of T for which this maximum occurs. So I will start by writing out the equation of the model given to us. Capital H is 3 plus 4 cos over half T minus 2 sine over half T. I will factor out the 2 here, so it's 2 times 2 cos a half T minus sine over half T, because this looks a lot like what we have just found in part A, with theta being replaced with 0.5 T. This means I can write this as 3 plus 2 root 5 cos of 0.5 T plus 0.464. And knowing that the cosine of any angle varies between plus minus 1, we can easily conclude that the maximum will be when we get a 1 here. So the maximum value for h max will be 3 plus 2 root 5, and this is meters. We need to include the units here. And then to find the value of t for which this maximum is attained, we need to say that cos of a half t plus 0.464 is 1. So cos of 0.5 t plus 0.464 is equal to 1. We know that the principal value we get is 0, and another value that could also work is 2 pi, and actually every 2 pi we get solutions. Now we are looking for a positive value for t, which means that if we go with 0, we will get something which is negative, because the rearrangement will be 0 minus the 0.464, and overall it will be a negative value for t. So I will instead work with the 2 pi, so 0.5 t plus 0.464 is 2 pi. So t is 2 pi minus 0.464 over 0.5, which turns out to be 11.6 seconds. In part C, we have to find the value of capital T, which is the time for which the point P is below water level. So if we think about it, as it goes around at this point and this point is exactly at water level, I will solve to find the times at which we are at water level, and the difference between these two will be the duration for which point P is below water level. So I start by saying that for P to be at water level, it means that capital H is 0. So when P is at water level, capital H is 0. So we've got that 3 plus 2 root 5 cos over half t plus 0.464 is 0, which means that cos over half t plus 0.464 is minus 3 over 2 root 5. This gives a principal value of 2.30611, which means that the 0.5t plus 0.464 is plus minus 2.30611 plus 2 pi k. I will split this one for the plus, one for the minus, so 0.5t plus 0.464 is equal to 2.30611 plus 2 pi k, and on the other hand I've got 0.5t plus 0.464 is negative 2.30611 plus 2 pi k. Remember, we're trying to find the first two positive values, so I will set k is 0 to get that 0.5t plus 0.464 is 2.30611, which upon rearrangement gives me that t is 2.30611 minus 0.464 and all of it over 0.5, which gives an answer for t to be 3.684926. And for this equation here, I will put case 1 to make the right hand side positive. If I go with k is 0, I will end up with a negative value for t. So setting k to be 1, we get 0.5t plus 0.464 is negative 2.30611 plus 2 pi, which means that t is minus 2.30611 plus 2 pi minus 0.464 and all of it over 0.5, which gives an answer of 7.02685. So the capital T that we were after, it was the duration of time for which the point P is below water level, is simply the difference between these two values of T. So 7.02685 minus 3.684926, which gives an answer of 3.34 seconds. Then in D, we are told that in reality the water level may not be of a constant height, and we need to explain how the equation of the model should be refined to take this into account. So let me go back to the diagram for you to explain a couple of things. We have already established that the maximum height was at 3 plus 2 root 5, and in a similar way of thinking, the minimum height is at 3 minus 2 root 5, at which point we are obviously submerged in water. Up to now, we've been assuming water level to be horizontal here. So it doesn't take long to realize that the point C here is assumed to be at 3 meters above the water level. So what's happening now is that we need to incorporate a more realistic scenario where the water level varies. So it could be something like this. So this 3 meters here is not fixed. And that's exactly the point we need to address. Now the examiner is not expecting us to come up with a mathematical improved model. We just need to qualify this improvement. So we incorporate the variation in water level into the equation for H by allowing the 3 to vary. We need to refer to the 3 here. We need to show we appreciate the fact that the 3 is the fixed height above water level for which the center of the wheel is found, and we need to allow this 3 to vary.